morning, students. In the last lecture, we introduced ourselves with the kinetic theory of gases. Now we are moving towards the next topic, which is nothing but the ideal gas and the real gas. But before that, we are going to see the behavior of gas and why the kinetic theory is needed for such explanation of the gases. So when a stone is thrown up into the air, it go to certain height and then return back to the surface. So the study of the stone, we can measure the velocity, kinetic energy under the laws of motion given by the Newton. Now in the case of gas, this gas is characterized by some parameters: pressure, volume, temperature. So it is impossible to study the motion of a single particle, and also the number of particles per meter cube of gas is around 10 to the power 23. So what is the number of molecules? It is approximately equal to 10 to the power 23 per meter cube. Means 1 meter cube of any gas contains about 10 to the power 23 molecules or particles. So this is a very large number, and in such large number it is impossible, it is very difficult to study the motion of a single particle. So what happened? Kinetic theory assumed that the average values of the physical quantities, and then it is applied to the macroscopic parameters. Therefore, this is the approach of the kinetic theory, the gases. So the behavior of gases can be explained very well by this kinetic theory. Now we are moving towards the ideal gas and real gas. So what is the ideal gas? We see here. This ideal gas? Ideal gas is a gas in which there are no intermolecular force of attraction between the molecules of a gas. Consider a gas in which there is no intermolecular force of attraction. Okay, such type of gas is as a ideal gas. So how we can write ideal gas? This ideal gas is the gas in which the intermolecular force are absent. Okay. What is the second property of this ideal gas? This ideal gas obeys the gas laws at every pressure and temperature. So, what are the properties of this ideal gas? The property of ideal gas are the intermolecular forces between the molecules of the gas are absent, and they obey the gas law at every pressure and temperature, or we can see also say that it obey the ideal gas equation, which is equal to PV is equal to nRT at every pressure and at every temperature. So this is the ideal gas. No gas in the nature is ideal. So there is another type of gas which is nothing but the real gas. What is real gas? In the real gas, the property of the real gas is that the intermolecular forces are negligible. Now, what is the meaning of negligible? Negligible means the intermolecular forces are present here they are absent, but in the real gas they are present, but the value of that intermolecular forces is very small, so we can say they are the negligible. And what is second, as we see in the case of ideal gas, this ideal gas obey the gas law at every pressure and temperature. In this case, this real gas obey this gas law at only high temperature and low pressure. Now what happens at high temperature and low pressure? At high temperature and low pressure, this real gas can behave like a ideal gas, because as the temperature increases or the pressure decreases, the intermolecular forces between the molecules also goes on decreasing, and they are absent. So we can say that if the intermolecular forces are absent, then it is nothing but the ideal gas. So this real gas can behave as an ideal gas in the condition of high temperature and low pressure. Or we also stated that no gas in the nature is an ideal gas. But if we take a real gas and we need to behave like the real gas, like the ideal gas, then what should we do? We should rise the temperature and low its pressure. Then this real gas may behave as a ideal gas. So in such conditions, high temperature and low pressure, this real gas may be act as a ideal gas, and this kinetic theory of gases is applicable. Assume that the gas is a ideal gas. Now we are moving towards the next topic, which is nothing but the free path. What is free path? We know that the gas molecules, when the gas is closed into the container, the molecules of the gas are not constant, they are moving randomly within the container. Now, while they are moving in the container, we also state that the number of molecules in a meter cube is equal to around 10 to the power 23. Then there is a possibility that these molecules collide with the other molecules as well as with the wall of the container. Now what happens when the single molecule is collide with the other molecule? Now we see that when a chemical formula, we see the chemical formula of any substances. For example, sodium chloride is equal to NaCl. There is a particular distance between the atom Na and the atom Cl. If we brought closer, we try to brought closer the molecules, the atoms of sodium and chloride, then there must be a repulsion between them. In this case, this also happen because when a molecule is approaching towards the another molecule, if the distance between them is very less, then there will be a repulsive forces arise between them, and therefore the collision between them is considered as the elastic collision. And due to this elastic collision, the speed and the direction of the molecules get changes abruptly. Abruptly means it changes on the large scale. This molecule also collide with the wall of the container, and as the molecules collide with the wall of the container, they exert some pressure on the wall. Okay, this how much pressure is exerted on the wall we are going to see in the next lecture. Now then what about the collision between the two molecules? Consider that this is a molecule and this is the another molecule. What happens? This molecule is traveling in this direction and they collide with this molecule. Then we are introduced a term called as free path. we introduce a term free path. What is free path? Free path is the distance covered by the molecule in successive collisions. Means if this molecule is traveling in this direction, the path followed by this molecule before collision, this path is called as the free path. Why it is called as a free path? We already stated that ideal gas, in the ideal gas the intermolecular forces are absent, so there will be no force acting on these molecules, so they are free to move within the container, hence this path is called as the free path. Now what happens when this collide? When this collide, it changes the direction and the speed of the molecule, and then what happens? Then the molecule may collide with the another molecule. So we introduce a new term again. It is called as a mean free path. It is called as a mean free path. What is mean free path? The mean or the average of the path covered by the molecule between the two successive collisions. For example, consider that a molecule is going into the very large number of collisions. For example, consider the molecule is here, then this molecule is going here, collide with this molecule, it changes its direction and come here, and again it's come here, then here. So in this way we see that there are so much of collision of these molecules. So if we consider that this is the free path, which is denoted by lambda 1, this is denoted by lambda 2, this is denoted by lambda 3, this is lambda 4, and this is lambda 5. So in this way, sometimes the distance between the two collisions is large, or sometimes it may less. So we are going to introduce a average value of that free path, which is called as a mean free path. And this mean free path is denoted by this letter lambda. What is lambda is equal to? This lambda is equal to lambda 1 plus lambda 2 plus lambda n divided by the number of collisions equal to n. Here we are considering there are 5 collisions, lambda 1, lambda 2, lambda 3, lambda 4 and lambda 5. So we can write here the mean free path lambda is equal to lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus lambda 5, and it is divided by the number of collisions, which is equal to 5. So by this formula we can calculate the mean free path. So in this lecture, what we see? We see the behavior of the gases under the kinetic theory, as well as we see the ideal gas, the characteristics of the ideal gas as well as that of the real gas. Then we see what is the free path, and then we see about the mean free path. Now this mean free path is depend upon some parameters, is depend upon some properties. On which parameters, on which quantities this mean free path depend upon? This mean free path is inversely proportional to the density of the gas. Means if the density is low, then the value of lambda is great. And this lambda mean free path is inversely proportional to the square of the radius of this molecule. Diameter d of the molecule. So if we write the equation for this lambda, what is rho is equal to, this rho is equal to the density, and what is density? It is the number of molecules in a given volume. It is equal to n by b. So we can write here this lambda is equal to 1 by under root 2 pi d square into rho, which is equal to n by b. So in this way, this is the equation by which we can determine the mean free path if we know the diameter and the density of the gas. So in today's lecture we see about the ideal gas and real gases. In the next lecture we are going to see derive the relation for the pressure exerted by the gas on the wall of the container. So this is all for today. Thank you. Have a